This is Act 3 of our crash course on optics, and we're going to revisit simple lens image problems and learn about ray tracing. So this is a beautiful candle. It is 1/2 of a meter to the left of a lens, and the image is 0.25 meters to the left of the lens. So there are several things that we already know without drawing anything out. So what we're saying is that if the object is to the left of the lens, and the rays of light obviously are converging at the object, that's where they start anyway. So if we're at the lens and the rays of light are converging 1/2 of a meter to the left, what is the divergence? Well, 1/2 a meter means the absolute value of the divergence is 2. The sign must be minus because it's to the left. The image is 1/4 of a meter to the left. So what is the divergence? 1/4 of a meter is 4. To the left is again minus. So if it was -2 coming in and -4 coming out, the lens must be a -2 lens. Now, that's not what's being asked. What's being asked is the image upright? So let's kind of work through that. So this is an example of an object to the left, an image to the right, and the lens in the middle. That's not what the problem was that we were just given. And the problem we were just given, both the object and the image were to the left. But I want to show you some lines here. These are both lines that pass through the center of the lens and therefore pass through undeviated. One of the lines starts out at the base of the candle and goes to the image's base of the candle. The other one starts out at the apex of the candle, where the flame is, and it also passes through the center of the lens. The way that I want you to think of it is this, is the line that starts out at the base of the candle is carrying information about the base of the candle. The ray of light that starts out at the flame is carrying information about the apex of the candle. If the image is to the right of the lens, then we just extrapolate these lines. They're straight lines because they pass through the center of the lens, therefore they emerge undeviated. If we have the image to the right, the image must be inverted. And I say that because, again, the line that carries information about the bottom of the candle is just going straight across horizontally, and the apex of the candle is now beneath that base on the right, showing us that it's inverted. But that's not the question we were asked. We were asked about this situation here, in which the object is 1/2 a meter to the left and the image is 1/4 of a meter to the left. This time when we follow the line through, and again, both of these central rays are central because they pass through the center of the lens. Both of these central rays are passing through the center of the lens. The top one's carrying information about the apex of the candle. Therefore, the image must be right side up. Ah, look at that. We are going to be talking about magnification later on in this lecture series. But I want to give you a little preview now. The image here is clearly minified. It's smaller than the object is. If the object is 2 feet tall, then this image is 1 foot tall. I know it's 1 foot because we've already described the base is one of the bases, from the object to the lens is 1/2 a meter, from the image to the lens is 1/4 of a meter. Therefore, the height of the image must only be 1/2 the height of the object. But that's the height. And the height is what we're talking about that is transverse or is perpendicular to the movement of the rays of light. Right, because the rays of light are moving from the left to the right, and we're talking about height. Height is up and down. There's also magnification or minification that goes along the axis of the ray of light as it passes through the lens, and that's called axial magnification. Axial magnification is transverse magnification squared. So in this case, the image is 1/2 the height. In truth, it's only going to be 1/4 the width. Nice slide, huh? So here is an example in which the image is to the right and the object's to the left. And this image is magnified by some amount. We're not going to calculate things out here. But if it's magnified, I don't know, let's say 3 times transversely, then what is its magnification going to be axially? And the answer is transverse mag squared. It is going to be some fat candle. Okay, let's come back here. A beautiful candle is 1/2 meter to the left of the lens. The image is 1/4 meter to the left of the lens. Is the image real? Well, we already know from Vergence, real and virtual. Real means that everything is on sides. Virtual means that it's off sides. So an object to the left of the lens, well, that's on side. That's going to be a real object. An image that is to the left of the lens, what's that going to be? It's off sides. It's going to be a virtual image. Now, this is the way that we often draw it. We're extrapolating these lines and all of this sort of stuff. But in truth, we really want to draw the lines that are not that represent our extrapolations just as dotted, because we recognize that that's not a real path of light. Also, the slide is wrong in that the lens here is drawn as convex. Of course, this is a case of a minus lens. It should be concave. So the 4 questions. The 4 questions that you can be asked, as I alluded to much earlier on in this lecture series, with simple lens object image problems are these. Where is the object or image, and what is the power of the lens? That's all sort of one question. 2, is the image real or virtual? 3, is the image upright or inverted? We just saw how to do that with central ray tracing. And 4, what is the size of the image? And we do that with central ray tracing too. We'll revisit MAG later on, but I want you to get the sense that you determine the size using central ray tracing and the inverted upright by central ray tracing. So we can divide these 4 problems, these 4 questions, into the first 2, which are handled with a Vergence diagram, and the second 2, which are handled with central ray tracing. Okay. More vocab. So this is a myopic patient who is a -5 myope, meaning that the correcting glasses that this patient needs is going to be a -5 sphere. His eye's obviously over plus. There's too much convergence going on. That's why we're putting up a -5 lens, a minus lens. So any way that we slice this lens, it is -5, and the rays of light converge in the vitreous. Well, what about this patient who is -5 plus 5 axis 180? So I've drawn the total power cross to the left, and we can take a horizontal section through the eye, and we'll see these red lines that are drawn. You can ignore the sort of dotted green lines. The red lines, and you see that they focus in the vitreous. Or we can take a vertical cross-section through the eye, and you see that these rays of light converge at the retina. If one of the rays of light, one of the sets of rays of light converge on the retina, then we're going to describe that astigmatism as being simple. If the other one converges in the vitreous, we're going to say it's myopic. So this is simple myopic astigmatism. It means that one of the focal lines is formed in the vitreous, and one of the focal lines falls on the retina. Simple myopic astigmatism. And with the total power cross, one of the arms has a value of 0, and one has a value that is minus. Compound means that no focal lines fall on the retina. Both of them fall on the same side of the retina. If they're both falling in the vitreous, then this is simple myopic astigmatism. -5 plus 2 axis 180 gives us a total power cross with arms of -3 and -5. Similarly, simple hyperopic, we see that one of the arms of the total power cross is plus, the other one is 0. And in compound hyperopic, both of the lines of the total power cross have got plus values. They're both in back of the retina, This is compound hyperopic, and mixed type is one in front and one in back. Okay, so we've run through all of these diagrams. This is our first lap. Let's take a second lap. Okay, so for our second lap, we can ignore the eye and look just at the total power cross. So what are the arms of the total power cross? One of them is the sphere, and one of them is the sphere plus cylinder, right? Mind you, not sphere plus half the cylinder. What's the sphere plus half the cylinder? That is the spherical equivalent, and that's, of course, the average of the two arms of the total power cross. So the two arms are the sphere and the sphere plus cylinder. So we don't need the diagram. All that we have to see is that one of the arms is 0 and one of the arms is -5 to know that it is simple myopic astigmatism. Compound, both of the arms, one is -3 and one is -5. Again, we're deriving that just by adding the cylinder to the sphere to get one of the arms, and then the other arm is just the sphere. Similarly here, plano and +8, and in the case of compound hyperopic, +8 and +3, and in the case of mixed type, +3 and -2. Let's take one last lap through, because the truth is, we don't really even have to know what the values are of the arms of the total power cross. All that we have to know is what the signs are. So if we look at the sphere is going to give you one of the signs. In this case, it's minus. The other sign is the sign of the sphere plus half the cylinder, which is 0. In this case, one of the signs is minus. It's the sphere. The other one is the sign of the sphere plus cylinder, which is also minus. So it's compound myopic astigmatism. In this case, one of the signs is 0. It's the sphere. It's plano. The other sign is plus. So that's simple hyperopic. They're both plus here, compound hyperopic, and one plus and one minus, mixed type. Do we ever use these words in clinical practice, mixed type, compound? Sometimes if I want to have a little flex in the letter that I write to a primary care doctor, I will use the words, but I wouldn't use them in front of an ophthalmologist. Okay, special topic, scatter. So Rayleigh scatter. Rayleigh scatter is what gives us the blue of the sky. My scatter gives us the white of the clouds. So let's talk about what gives us each of these things. In the case of Rayleigh scatter, the particles that are scattering the light are much smaller than the wavelength of the light. And in scattering the light, the short wavelengths are scattered preferentially more than the long wavelengths. So the blue ones spread out to fill the sky, whereas the ones that are less blue make it here to Earth. Rayleigh scatter, wavelength preferential, short wavelengths get scattered more than the long ones. In my scatter, or me scatter, I don't know how to say it, there's a very, very small predilection towards scattering short wavelengths more, but in fact, all the wavelengths get scattered relatively equally, which is why the clouds are white. White light does not split up with my scatter with the clouds. It does split up with Rayleigh scatter with the blue of the sky. This is a famous picture, a painting, and we see the sun coming in through the oculus in the dome there, and then it is shown on the wall. It's a painting. In real life, it looks like this. This is a photograph on the right. What is the difference between the one on the left and the one on the right, other than the funny clothes that the people are wearing on the left? It's that you can see the beam of light as it's coming in through the oculus, through that hole there. And that is called the Tyndall effect. We see that if you're in a movie theater that's smoky and you see the path of the light through the smoke, or you see it when a patient has flare. Flare is an example with the slit lamp of the Tyndall effect. Ooh, another special topic. Brewster's angle. This has nothing to do with Brewster. It's actually Euclid with an angle. These are two pictures taken of the same window. The one on the right is taken with a polarizing lens, and the one on the left is not. So the reflection is completely cut out with a polarizing lens on the right. It's not partially cut out, it's completely cut out with the polarizing lens on the right. What does that tell us? It tells us that the reflection coming off of this window is polarized. Now, all light, as it bounces off of an interface, has some preferential polarization. So we know here, the angle of incidence is equal to the angle of reflection, and then this is the refraction. All of these things happen at the same time, unless we're greater than the critical angle, something like that. But otherwise, reflection and refraction always both take place. So this is coming in at an angle of theta. And let's say that the incident light is not polarized, meaning it's polarized in all directions. There's no polarity to it. When the light reflects, it reflects preferentially polarized, but at a special angle, it reflects completely polarized. And we call that special angle Brewster's angle. And this, again, is an example of a photograph that is taken exactly at Brewster's angle to the mirror, to the window, allowing a complete invasion of privacy of your neighbor's house. Okay, so I promised you that we would revisit anisometropic anisophoria, and we're going to do it this time with spherocylinders, with astigmatic lenses. Okay, so this patient has spectacles, -5 + 2x is 90 in the right eye, -5 + 6x is 180 in the left eye. He's looking 2 centimeters down from the center of his lenses, and he is diplopic. Okay, so we're going to draw out the total power crosses for these two lenses. 90 and 180, very convenient for us. And 3 and 5, take a second, look at that, make sure that you would have come up with the same values for the same arms of the power cross. If we're looking down from the optical center of the lens, then the only arm of the power cross that we're interested in is the vertical arm. If we're looking sideways, we'd only be interested in the horizontal arm. So the lens on the patient's right, on your left, the patient's right lens, is as if it were a -5 sphere. If we're just looking down, we can ignore that -3. And the other eye is as if it were a +1 sphere. And in this case, we are getting, by Prentice rule, because we're 2 centimeters down, 10 prism diopters in the right eye and 2 prism diopters in the left. Now, what's the base? Well, we're going to take vertical cross-section, since, again, we're only working through the vertical portion of these lenses because we looked vertically down from the optical center of the lens. We are going to take vertical cross-sections through the lens. So the right eye is a -5. What does that look like? Minus lenses are thinner in the middle, so they are as if they were 2 prisms oriented apex to apex. We're looking down, therefore we're in the 10 base down portion of this lens. In the left eye, it is plus in its vertical cross-section. Does it matter that it's minus in its horizontal cross-section? No, I don't care. It's plus in its vertical cross-section, which means it's as if it were 2 prisms oriented base to base. Therefore, we are in the base up portion of that prism. So we are obtaining 10 base down in the right eye and 2 base up in the left eye. So what's the total? The total is 12, not 8. The total is 12. Okay, we talked about chromatic aberration. There's another sort of aberration that's of interest to us called spherical aberration. For spherical lenses, the powers that we calculate, that sort of delta n over r, that's really only for paraxial rays, for rays that are close to the optical center of the lens. The further afield we get, the further out from the optical center of the lens we get, the more refractive power that lens has. And it is going to cause the rays peripherally to focus to have more converging power, to focus closer than the paraxial rays. This is called spherical aberration, and it's correctable by using an aspheric lens, a lens that is flatter in its periphery than in its center. Nothing to calculate here, just to know spherical aberration. Minus lenses are more minus in their periphery than they are towards the center. Plus lenses are more plus in the periphery than they are towards the center. Here's something else that we don't have to calculate. It's astigmatism of oblique incidence. This is the way that I think of it, and tell me if this sort of helps you. Let's have you hold a coin of your choice, or a frisbee if you're that type, so that the coin is vertical. And imagine this coin to be a lens. Actually, if you've got a lens, a 20 diopter lens, you can hold a lens like this. And then let's tilt the lens a bit about the horizontal axis. So the way that I think of it is this, is we've changed the horizontal curvature only minimally, but vertically we've made it more curved. We've in essence compressed the whole curvature of the lens into a smaller vertical space. That is going to give the lens more power vertically than horizontally, or it's going to make it an astigmatic lens. In the case of a plus lens, it is going to make the lens more plus vertically if we tilt it about the horizontal. In the case of a minus lens, it's going to make it more minus vertically as we tilt it about the horizontal. It is going to make it more of whatever it is vertically as we tilt it about the horizontal. Now, what is the axis of the cylinder? Well, if it's acting vertically, then the axis must be horizontal. Conveniently, the axis of the cylinder of the axis of the astigmatism of oblique incidence is the axis of rotation of that lens. Okay, once more, nothing to calculate here. Why does it matter? It matters if you're doing retinoscopy on a patient who's not looking at you but looking to the side. You can get astigmatism that is not actually there. There are other special circumstances in which we encounter astigmatism of oblique incidence. Okay, so here's something you're going to hear from no one else, unless they learned from me. This could be a really challenging problem. The patient who wears -4 +5 axis 90 wears the spectacles, looks up at a star in the sky. What is projected on the retina? It's a point, it's a star. But what about when they take the glasses off? What is the image on the retina then? Well, we can draw out the total power cross and say, well, this part of the conoid of Sturm intersects the retina, therefore it must be this, it must be that. It's, a line, an oval, axis, this way, that way. There's another way to view it, which is this. Imagine two lenses. Let's say one lens is a -4 and one lens is a +1. A patient is a -4 myope, and another one is a non-accommodating +1 hyperope. Both of them take the glasses off and look at the star. Both of them are going to have blur circles. But which one is going to have the larger blur circle? The uncorrected +1 or the uncorrected -4? The answer obviously is the -4 is going to have the larger blur circle. Even if the +1 doesn't accommodate, 1 is less than 4, so the blur circle is going to be smaller. So what we're going to do is we're actually going to plot this out. And we're going to say, okay, horizontally, this patient has got 1 unit of blur. Vertically, this patient has got 4 units of blur. We ignore the signs. We're just looking at the absolute values of the diopters of the total power cross. And we connect the dots. And this person, when he looks at the sky without wearing glasses, will see an oval with its long axis vertically. What about this person? -4 +4 axis 90. 4 units of blur vertically. 0 units of blur horizontally. What is this patient going to have projected onto his retina? The vertical focal line. This special topic on topography, I am going to blow through really quickly because I have a 4-lecture set series on topography and wavefront, and you can see things in much greater depth there. But the objects of interest to us are pizza, bagels, and Schweppes Bitter Lemon, which is my favorite soda, which unfortunately is not sold in the United States. Sad. This is a one-step keratometer. This is the sort of keratometer that you are used to using. The assumption that this keratometer makes is that the meridian of greatest flatness of the cornea and the meridian of greatest steepness are orthogonal, that they're perpendicular to each other. This is a Javal two-step keratometer, which makes no such assumptions. At Mass Eye and Ear, where I did my cornea fellowship, we had some of these. I don't think I've seen them outside of that clinic, though. Okay, so this is a patient with, this is a topography of a patient. This is a patient with keratoconus. Red here means steeper, blue means flatter. But what is the keratometer going to tell us about this? Well, it's not going to be able to pick out the cone. Yes, you can look at the shape of the Myers, but all that it's going to tell us is what the cylinder is. Certainly, if you do an auto refraction on this patient, get an autokeratometry, all that you're going to get is the cylinder, not an indication that that the patient has any abnormality of the topography of the cornea. Well, one way to assess it, one qualitative way, is to cast some rings on the patient's eye and to look at the spacing of the reflections, the first Purkinje image, the reflections of the rings coming off of the eye. And because we have to get close to the patient, we're going to put a little plus add in the middle of that placido disc so that we can see through things. This is a Maloney keratometer. It's an intra-op keratometer that projects rings on the cornea. This is a Jedmed Van Lunen keratometer that you use with the slit lamp to illuminate the rings. And this is a Klein keratometer, which is a placido disc that's illuminated. Okay. These are rings that are projected onto a patient's cornea. What astigmatism does this patient have? I don't know. They all look pretty round from here. What I do want you to notice is that the spacing between the rings is relatively even. What about this patient? So some of the rings are spaced more closely than others are. If you picture the difference between a marble and a shiny bowling ball, if you project a set of rings onto the marble, you'll see, if you look through the marble at a placido disc, you'll see all of the rings through that marble. And all the rings will be small because the marble is small. If you do the same thing with a bowling ball, the rings will be more spaced out because the bowling ball is bigger, has a flatter curvature. So steeper curvature, as is the case with the marble, you see the rings packed more closely, and flatter curvature more spread out. This cornea is flatter vertically at steepest, sort of down and to the right in your view there. The problem with placido discs is that they're ephemeral. You take a look, but there's nothing to record. If you attach a camera to the back of a placido disc, you get a photokeratoscope. And there's also on the website an interesting number of videos on a clip-on photokeratoscope for mobile phones, but that is a topic for another day. So astigmatism, what would 2 diopters look like, or 4 diopters look like? They look pretty round. 4 diopters is about the limit where we can tell that someone has astigmatism by looking just at the ring. So when we're using a placido disc, or we're projecting Myers, we are only able to see really the grossest things. So this is a patient who has had some sort of refractive surgery, is flat in the center, is steep in the mid-periphery. And the reason that we don't trust keratometry for these patients is that keratometry measures at an average of a 3 millimeter annulus on the cornea. It does not measure the central cornea. So for someone with a refractive surgery, certainly for this cornea, you're going to get an estimation that the cornea is a lot steeper than it actually is in the patient's visual axis. Why does this matter? Are you going to prescribe the wrong glasses? Or if you manifest the patient, probably not. But if you're going to be doing cataract surgery on this patient and you plug in the wrong keratometry value, you're going to make this patient badly, hyperopic or myopic? If we're overestimating the power of the cornea, we're going to put in an IOL that is too weak. The eye is going to be underplussed, so it's going to be a hyperopic eye. Be bad news. Okay, so instead, we can do things quantitatively, like corneal topography, and we described before the issues with the can and astigmatism. We're going to revisit them briefly, and we're going to talk about the patterns that are induced by the fact that we do our measurements radially through the cornea, and I'll show you what I mean. So this is a round cornea. This is a fairly spherical cornea. This is also a fairly spherical cornea. We can discuss on one-on-one how to interpret topography, but there are very few colors in this map. So most of the cornea has one or two of the same colors. So this is an eye that does not have a lot of astigmatism. This is an astigmatic eye. This is with the rule, and this is an eye that is steep vertically and is flatter horizontally. I want you to see there's a sort of a bow tie pattern or an hourglass pattern here. And this is an eye with asymmetric astigmatism. So whence comes this bow tie pattern? We said that this is an astigmatic patient. This is a with the rule patient. This is actually a topography of one of my former residents. Very nice woman. This patient has got with the rule a astigmatism, which means that the correcting lens is going to be a spherocylinder, that the cornea must be a spherocylinder. If it's a spherocylinder, why does it have this hourglass shape? And it's because what we're looking at on the left, even though we call it topography, is not really topography. We're not looking at the shape. We're looking at the curvature, at the power. It's a power map. It's with the rule. Is the bitter lemon can on the right with the rule or against the rule? Well, I've oriented it against the rule because its curvature is horizontal. Vertically, it's got no curve. So this is the Schweppes, delicious Schweppes bitter lemon, oriented horizontally. Horizontally, it is at its flattest, as I'm showing, drawing this line through the Schweppes bitter lemon, and indeed the cornea on the left is at its flattest horizontally. Vertically, it is at its steepest, and that's indicated by red, as is the cornea on the left. And at an oblique meridian, it's going to have some intermediate power, which is shown as green. If we add up all of these powers and fill in the gaps in the middle, then we're going to get that bow tie pattern that we see on the left. It is a bow tie pattern because it is a description of power, and as a description of power, all of the power lines are drawn through the center of the cornea. They're drawn radially like little pizza slices, and that's why a topographic cylinder can produce a power map that is a bow tie, even though we call it topography. This is a brief, moderately esoteric point that I'm just going to go through quickly, which is that even in the topographers, there is a hole in the middle, as with a bagel, that is where the camera is that captures the image. So the center of the cornea with the placido disc-based topographer is actually not going to be measured, and there can be significant features in the central cornea that are just not seen. The other thing is that there are two sorts of maps that are produced by topographers that are called axial maps and tangential maps. Axial maps are the maps of the curvature. We've already said that the curvature in our mapping has to go radially through the center of the cornea. We can further constrain it by saying that the curvature has to pass through the optical axis of the patient's eye. That gives us an axial curvature. Or we cannot constrain it and say, well, we're just going to fit the best possible curve to any feature on the cornea, not constraining the curve to pass through the axis. We call this a tangential map. In clinical practice, we tend to use axial maps more, probably because they tell us more about the effect that a topographic feature is going to have on the patient's vision, the effect it's going to have on the optical axis. It's an axial map. The tangential maps are better for geographically locating features on the patient's eye. So this is a patient with keratoconus. We can see the optical effect of the cone on the left, but we can see the extent of the cone with the tangential map on the right. Again, axial maps are what you're going to mostly see. Again, axial versus tangential map in a patient with PRK. Tangential maps are better at localizing features. And this is an orb scan which shows us the map that we're used to seeing on the lower left, that astigmatic map, but it also shows us our true topography, which is on the upper left, the anterior float, which is the combination of a sphere and a cylinder, and sure enough, it looks like a sphere with a cylinder. The one on the upper right is the back curvature, and the lower right is the optical pachymetry. Another special topic, coupling. Okay, this is an eye with a suture in it. And the question is the suture making this eye, this is a tight suture, is this suture making this eye steep horizontally or steep vertically? Is this tight suture going to flatten things or is it going to steepen things? So I'll give you a second to think about it. And then I'm going to tell you how to think about it. This tight suture is going to actually make things steeper in the direction of the suture. It's going to make things steeper vertically because this is a vertically oriented suture. Now, if you imagine a suture as being like a Band-Aid, where there are two places where it's sticky, right? The two places where it sort of enters the cornea. Now, picture having a balloon, and this balloon is spherical. And you're going to take a Band-Aid and you're going to stick the Band-Aid on, vertically on it. You're going to pull the Band-Aid really tightly and stick that back down. That is going to make your spherical balloon sort of hot dog shaped. But where is it going to be hot dog shaped? Where is it going to have its greatest curvature? It's going to have its greatest curvature in the direction of orientation of that Band-Aid. And the same thing is true of the cornea. So sutures make things steeper, and sutures act in the direction of the suture. Compare that to incisions. Incisions do not act in the direction in which they were incised. They act perpendicularly to it. So this incision is going to spread out horizontally. It is going to flatten things because incisions flatten things, but it's going to flatten things horizontally, not vertically. Now it's going to flatten it horizontally locally there. In order to distribute things more evenly, we're going to want to do a bunch of incisions, which are going to flatten the cornea. And in doing so, it's going to treat this patient's myopia, and this is radial keratotomy. So there is an area of flattening centrally. Okay. Here's a question. If this suture is steepening the cornea vertically, what is it going to do to the cornea horizontally? Is it going to have an effect horizontally? Let's say that this eye were an eye that, before the suture was put in, was 44 diopters vertically and 44 horizontally. We put in this suture and this patient is now 45 vertically. Is the patient still going to be 44 horizontally, or is he going to go down to 43? And the answer is this, is as long as the lines of force are passing through the center of the cornea, they're going to be coupled, meaning that anything that you do to one meridian, you're going to do the opposite to the other one, and the average power of the cornea will remain the same. So if this cornea was 44 and 44, and is now 45 vertically, this cornea is going to be 43 horizontally. We say that it is coupled, and the average power is still going to be 44. This is an example of an incision that is coupled. So this incision, this little smile down there, this arcuate incision, is at every point the forces, since the forces act perpendicularly to the direction of the incisions, the forces at every point are going to pass through the center of the cornea. This is an incision that is coupled. So it is going to cause flattening vertically, and it's going to cause steepening horizontally, and the average corneal power should remain the same. This is a horizontal incision that is not coupled, or not completely coupled. It's coupled in the center, but it is not completely coupled out in its periphery. We can think of the periphery as sort of a geometric addition of an incision that is coupled and another horizontal one that is not. So this is going to create some flattening, as all incisions do, but the average power of the cornea will change because some of the flattening will not be coupled, and this patient will wind up being slightly more hyperopic as a result of this incision than he otherwise would be, in addition to the change to his astigmatism. Okay? Or in other words, this is equal to that plus that. Okay, accommodation. This is an emmetropic patient. This is a myopic. This could be a myopic patient in which there's a far point. But in essence, an emmetropic patient who's accommodating is sort of making himself myopic, is adding extra plus. And that extra plus allows him to focus on something near. The most accommodation that patient can dial in, the maximum, is going to allow this patient to see an object at a particular point in space. If it's the maximum, we refer to that as the near point. Now remember, myopic patients have far points, a point beyond which they cannot see. They also have near points that are set closer than the far point. We'll put numbers to these things shortly. For a mildly hyperopic patient, there will be still a near point. The far point is in back of the patient's head. But some of the accommodative effort that the patient is going to put forth is just going to be to correct for that hyperopia. What's left over can contribute to the near point. In someone with high hyperopia, even maximal accommodation will not overcome the hyperopia, and the near point will be in back of the retina. It won't be as close to the retina as the far point is, but it will be in back, and indeed this patient accommodating will not be able to see anything even at distance clearly. Okay. Distance vision in an uncorrected mild hyperope. The mild hyperope is going to accommodate a little bit in order to overcome the hyperopia. So words. The far point, the point from which rays of light will have a divergence equal to the refractive error of the non-accommodating eye, if we assume accommodation occurs at the surface of the cornea. That's an assumption that this makes. Or it is the point at which rays of light upon entering the non-accommodating eye will focus upon the retina. The near point is kind of its cognate, but with an accommodating eye. Accommodative amplitude is the difference in divergence between the far point and the near point. Now keep in mind, the far point for hyperopic patients is in back of the eye, and the near point can be too. So the accommodative amplitude is this difference in divergence. However, patients cannot see in back of their heads, so the accommodative range is in real space what the patient can actually see. So for, let's say, a -2 myope, whose far point is at half of a meter from him, with 4 diopters of accommodative amplitude, that person has a near point that is 1/6 of a meter, right? They have 2 diopters from their myopia and an additional 4 diopters from accommodation gives a total of 6. Their accommodative range will be from half of a meter to 1/6 of a meter in front of their head. What about a +2 diopter hyperope with 4 diopters of accommodative amplitude? Well, that hyperope is going to have to spend 2 of those diopters, 2 of those 4, just on correcting the hyperopia, and we'll only have 2 left over to produce the near point. The near point's only going to be at half of a meter from him, and his accommodative range is going to be from infinity to half of a meter. What about a plus 10 hyperope? That person is going to have no accommodative range at all. Okay. Accommodative amplitude by age. This is just a sort of a rough scale. Give you an idea of the sort of adds to give patients based on this sort of stuff. Nothing really to memorize here, except to understand that loss of accommodation is not linear. Okay. This is complicated, and I'm going to tell you right now that this is difficult, and you can either choose to get the gestalt and not understand it, or you're going to have to, I'm sure, view this more than once in order to really get it. So this is a -3 myope, and -3 myope means that the patient wears -3 spectacles. It doesn't mean that the vergence that the patient desires is -3 on his cornea. It means that the patient wears -3 glasses. So we know from correcting ametropia, from correcting glasses, that the secondary focal point of the correcting glasses has to correspond in space with the patient's far point. This patient's far point is therefore at 1/3 of a meter to the left of the spectacle plane, not to the left of his eye, but to the left of his spectacle plane. I've chosen a fairly average vertex distance here of 1.2 centimeters. That's the distance between the spectacles and the patient's cornea. The vergence of the rays of light hitting the patient's cornea is -2.9. Right, so that's what it is. For a hyperopic patient, a plus 10 hyperope, if we do the same sort of calculations, we're going to find that the vergence of the rays of light striking this patient's eye, 10 centimeters minus 1.2 centimeters, 1 over that, is 11.4. Okay, let's revisit these patients with accommodation. And I'm going to put our near target, not 1/3 of a meter from the patient's eye, but 1/3 of a meter plus 1.2 centimeters from the patient's eye, because it's going to make calculations easier. So this is an emmetrope. How much does this emmetrope have to accommodate to see this object that is at 1/3 of a meter plus 1.2 centimeters? It's 2.9 diopters. We did that calculation when we were looking at the myopic patient. So what of the myope? This is a -3 myope who's also looking at an object that is 1/3 of a meter from the spectacle plane. Just like the emmetropic patient, we put our object at 1/3 of a meter from the spectacle plane, even though the patient's not wearing spectacles. That's why it's 1/3 of a meter plus 1.2 centimeters. Here, the object that the patient wants to see is in the same place. It is 1/3 of a meter from the spectacles. That means that the rays of light hitting the spectacle is going to be -3, exiting the spectacle is going to be -6, and is going to encounter the cornea with a vergence of -5.6. You can do that calculation on your own. -5.6 is what the rays of light are that are striking this cornea. What is the vergence that the patient wants if he's a -3 myope? And the answer is -2.9 diopters. We know this from several slides ago when we looked at what the vergence was for the rays of light that the -3 myope actually encounters. So 2.9. So this patient has 2.9 and it needs the 2.9 to compensate for his myopia, is encountering 5.6. The difference of 2.9 and 5.6 is equal to 2.7. So this myope wearing -3 spectacles is only going to have an accommodation equal to 2.7, which is less than the emmetropic patient who needed to accommodate 2.9. So only 2.7 is needed for the -3 myope. What of the plus 10 hyperope? So we saw that the plus 10 hyperope actually needs to have plus 11.4 hitting his cornea. Again, that was several slides back. Welcome to go back and to look at why it is 11.4. The object is 1/3 of a meter to the left of the lens. It's going to hit the lens with a divergence of -3, exit the lens with a divergence of +7, hit the cornea with a divergence of +7.6. 7.6, so 11.4 minus 7.6 means that the hyperope needs to accommodate 3.8. So hyperopes wearing spectacles need to accommodate more than emmetropes, who need to accommodate more than myopes wearing spectacles for objects at the same distance. That's the gestalt. If you want to know the math, I'm sure you're going to have to view this again. Special topic. Okay, so for this topic, I need you to turn the lights off in your room. And if you're viewing this on the phone has to be some distance from you, maybe, I don't know, 3 feet. If you're viewing this on a monitor, then just sort of step back from the monitor, but it's got to be in a darkened room. So we're going to talk about chromostereopsis. So this is what I want you to look at. And what you should be able to see is that the red print looks closer to you than the blue print does. It looks like it's in a plane that's a little bit closer than the blue plane. Blue plane. So take a couple seconds, convince yourself that that is a fact, and then we're going to talk about why that is. And this is called chromostereopsis. So this is an emmetropic eye looking at something that is at distance. This is an emmetropic eye right before he has accommodated to see an object that's at near. So there's an object that's at near, and it is focusing in back of the patient's retina, and now he's going to accommodate in order to bring that image onto the retina. So this is a signal that the object is close. It is close. It is focusing in back of the retina. So let's go back to our chromatic aberration duochrome diagram, and we see that the red focuses in back of the retina and the green in front. That red is going to be focused in the same way that a close object would be focused and will be interpreted as being close. And the green will be interpreted as being far. And that is exactly what we see when we look at our hither and thither slide, where the hither is close and the thither is far. Do you guys know what hither and thither means? When do you hear it? She gave a come hither glance or something like that. Hither means to here, and thither means to there. And that is the end of Act 3. Only one to go.